Good morning, everyone. My name is Amal Kiruji. I am a PhD student in the French Alternative Energies and Atomic Energy Commission, and today I'm going to talk about our work entitled DEISA for Dask-Enabled in Situ Analytics. This work has been done with Julien Bigot and Bruno Raffin. As we all know, there is a widening performance gap that is separating I/O bandwidth and the CPU performance. In some fields such as weather forecast, the traditional post-hoc processing is not feasible anymore due to the limits in both storage capacity and I/O duration. In-situ approaches are attractive to bypass the disk accesses and fully leverage the HPC platform as they process the data as they are generated instead of writing them to disk, then reading back them for post-processing. However, in-situ workflows are more complex to set up than post-hoc. This often requires significant efforts to adapt an existing post-hoc data analytics code to work in situ. That's mainly due to the fact that in-situ tools are usually built on MPI programming model inherited from the host simulation. Thus, the user needs to explicitly specify the resource allocations, the communications, and the task scheduling. While MPI is well suited for scientific applications where we have regular schemes, usually computations, communications, and sometimes global synchronizations, MPI is not the most suited for irregular applications. An irregular application is characterized by irregular data structure, control, and communication patterns. What we mean by MPI is not the most suited for this kind of applications is that using it become quickly really complex to use. A known example for this kind of applications is parallel data processing algorithms. For those, higher level programming models and paradigms and higher productivity languages are preferred. Several questions can be raised here if we take the in-situ paradigm as a solution for the I/O bottleneck. The first one is, what can be done to reduce this complexity while setting up the in-situ workflows, specifically from the application community point of view? The second point is, if MPI is not the most natural model to write the in-situ analytics, then which paradigm should it be? To answer those questions, in this paper, we propose to bring together bulk synchronous parallel paradigm, which is implemented here through MPI, and the task-based programming model in an in-situ workflow. Concretely, we do that by coupling MPI simulations to task-based in-situ analytics using Dask, and that's done through DEISA for Dask-enabled in-situ analytics. But before getting into details about DEISA, let's introduce first Dask. So Dask is a Python framework that is built on a task-based programming model, which is here distributed actually, where the user writes almost sequential code, and Dask manages the parallelization, the task scheduling, and the different communications too. Among other Python frameworks, we have chosen Dask because of the parallel versions of well-known libraries it provides, such as NumPy, Pandas, and Scikit. Such a characteristic is really important for us, as even if we will move from sequential post-hoc Python codes to parallel in-situ analytics, we will not change the scientific habits nor the way the scientists write his analytics. And here is an example of how Dask works. So in the right side, we have a scheme. Let's focus on it first. So here we have a complete Dask instance and a parallel file system. So we suppose that the simulation already has already written the data into the parallel file system. And we have a Dask instance here with a client, a scheduler, and workers. So the idea here is that the analytics client in Dask is the entry point, and it does not read all the data to the analytics client, then submit to Dask scheduler. It only reads some metadata from the Power File system. And then we can check actually the code here to see how things are done concretely. So the first thing that we do is to connect this client to the scheduler. Then we read some metadata, the descriptor of the data set that we want from, for example, here data.hdf5 file. Then we're going to use this descriptor to create a Dask array lazily. And the creation here is just the descriptor of this Dask array, not the actual data. Once this is done, we can use it to, for example, here to compute an incremental PCA in Dask. So once this is done, actually, the task graph is submitted to the Dask scheduler, and then it will send different tasks to different workers. And it's only at this point that the data is really read from the parallel file system. Now let's talk about DEISA. Notice that we have the exact same scheme for Dask, where we have a client, a scheduler, and workers. However, we don't have anymore the parallel file system as a source of the data, but we have a running simulation as a source of the data that is feeding the Dask workers with the data that is generated. To ensure the coupling between these two separate parts, we have added two main components: a DEISA bridge per process and a DEISA metadata adapter in the client side. How it happens is that at each time step, or every time the simulation generates data that it wants to send to Dask to be analyzed, this data is sent directly to the workers. And a set of metadata is sent also to the scheduler. Those metadata describe the sent data to the workers. Then this metadata can be fetched from the client side and used to create Dask arrays. Those Dask arrays then can be used as any ordinary Dask arrays in Dask, and then tasks are submitted to the scheduler, and then the scheduler sends those tasks to the different workers. Two small remarks that we have to say here is that by default, task granularity in DEISA is defined by the size of the data generated by the MPI process. That's fine if the data is around 250 megabytes. However, we may need to recheck the data in Dask once we have the Dask array. So by default, we don't do this, but this can be done easily by adding only one line of code in the analytics script. And another point is that we use a round-robin scheme to do the data redistribution between the MPI processes and the Dask workers. And for now, it works really fine. Okay, so that's done. Now let's go and see how things are done in the DEISA metadata adapter, and how things are different from the post-hoc version. So let's remind first the post-hoc version how it is. So we do different imports, we connect the client, we read the data here. So the source is the file here, and then we use the data. In DEISA, the only thing that will change is actually importing data and getting the data from the adapter instead of reading the data from disk. And it's the only line that will change from the analytics part. Awesome. So now let's see how things can be changed, how things are changed in the analytics, in the simulation part. And before doing that, we're going to talk about PTA. let's notice first thing here. So between the process and the DEISA bridge, there is a small component here, which is PDI. So what's PDI? PDI data interface is a thin interface designed to decouple I/O concerns from the simulation code. It consists of three main things. So there is calls to PDI expose in the simulation code, in our code, so that we make the data available to PDI and the plugins. There is a YAML configuration file where we describe the data layouts and the plugins. And finally, the plugins themselves, where we do the actual job. And for example, here we have a list of plugins such as HDF5, PyCall, NetCDF, and so on. Concretely, how that's done in post-hoc. In the left side, we have a C code that is instrumented in PDI. In the right side, we have a configuration file. So let's start first with the C code. So what we do is to initialize PDI, and then use PDI multi-expose, for example, to expose here the configuration and the rank. And we do that by emitting an event which is called init. And for example, at each time step, we're going to share also the time step itself and the temperature file. And finally, we call PDI finalize at the very end. So that's only the thing that we have to add in the simulation code. And actually, by just adding that, we can use multiple plugins to process the data. So this part is really independent from the processing that we were going to do. And that's the decoupling part of the simulation from the processing or the IO stuff. Let's see now the YAML configuration file. So here in the YAML configuration file, we have three main parts. We have the metadata, the data, and the plugins part. The difference between the metadata and the data part is that the metadata are small data that PDI, of which PDI keeps a copy. And the data, they are mostly references to the actual data, and PDI did not copy those. Do not copy those. Yeah. And in the data itself, we have two parts actually. There is a description of some virtual arrays, and I'll explain what we mean by that. And a part where we describe the main fields or the real data. And let's start by the real data. So PDI is local to each process. And the data that we describe here is actually what is generated by the process. For example, here we generate temperature field. So we describe this temperature field here. We say that is an array of doubles. That's the size. And it is mapped to some virtual array. And the size of this slice, if we can say it like that, is one with the same sizes here. And it will start at the step, at a given time step, and at a given position that depends on the rank. So the virtual array actually is a global description of all the data that is generated by the simulation independently from the process and the time. So we take care of putting a new dimension here and X and Y, for example, for the 2D file. So this actually describes the total data generated by the simulation, and it is virtual because we don't have it we cannot have it in memory at once. We only have one time step at once. So that's the data description. And finally, the plugin part. So here, for example, for the post-hoc, to use Parallel HDF5, we need the MPI plugin and the DECL HDF5 plugin. We have some parameters to add. So we give the name of the data that we want to write. You give the action that we want, for example, to write or to read. Here, we want to write. The name of the data that we want to write and when we want to write it, and also the communicator that we need for parallel HDF5 writing. So that's actually how it's done for post-hoc. Now, if the simulation is instrumented with PDI and we already have the configuration file, what we need to do for DEISA is only to change the plugin part, and that's how it will become. So the plugin part, I only need DEISA. In DEISA, there is two main keywords. We have the scheduling file. So here, the scheduler file, sorry. That's a JSON file that contains the address of the scheduler in Dask, and a transfer keyword to say that I want to transfer the GTEM field when the time step is greater than 0. So as you have noticed, for the simulation file, for the simulation code, once it is instrumented for post OC, it will not change, and we can use the exact same instrumentation and the exact same data and metadata configuration. So the only thing that will change again is the plugin that we are using. Let's talk now about the performance evaluation. So we have done the evaluation of our paper in Rush supercomputer that has 192 nodes, an omnipath, NoWork, and GPFS, sorry, disk. And to evaluate the performance, we have implemented two mini apps. From the simulation side, we have used a 2D heat solver, and we have added from the analytics side an incremental PCA that already exists in Dask. Actually, we have only used it. Now that we have achieved the first goal, as I have already mentioned regarding the ease of use, let's check the performance. Here are weak scaling timings for 3 versions, MPI simulation without IOs in the left, DEISA in the middle, and post-hoc with Dask in the right. The MPI simulation part is represented in blue. For the 3 cases. For DEISA, we have the data and metadata transfer in red. For post-hoc, the data writing to the DIX is in beige. The gray part in DEISA includes waiting for the data to be available and the computations themselves. For the post-hoc, it includes reading the data from disk and processing it. The analytics and the simulation in DEISA are executed concurrently. It's done in situ. For the post-hoc, however, the analytics are done at the end of the simulation. We have fixed the data size per MPI process to 128 megabytes, and we scaled from 128 up to 512 MPI processes from the simulation, and 16 workers to 64 from the analytics side. And all of this configuration is described in the table in the left side of this slide. So regarding the results, as shown in the figure, DEISA performs and scales better than post-hoc version. It is more stable, and it only includes an overhead of at most 23% compared to the simulation without any IOs. The variability here that we see in the writing the data to disk for the post-hoc case can be explained by the fact that we are sharing the parafile system with other users. Then what can be said also is that DEISA is three times faster than post-hoc version if we include only the MPI part, which means that we have the MPI computations and the writing to disk for post-hoc, and for DEISA is only transferring the data and the MPI computations. And it is 16 times faster if we include also the analytics here for post-hoc. So in terms of performance, with almost the exact same efforts, we are achieving better and really better performance compared to post-hoc. So here are all the results. We went into details to see where times are spent and how DEISA behaves in small and large tasks, and the results are shown in these two figures. In the left side, we have fixed the amount of data generated by each MPI rank to 1 megabyte, and we fixed it to 56 megabyte in the right. Those sizes will determine the task size in Dask, the task granularity in Dask. In the left of each figure, we used 100 processes and 16 workers, and in the right, we scaled up to 512 processes and 64 workers. We notice for small data that the analytics iteration is longer than the simulation iteration. This can be explained by the inefficiency actually of Dask handling small tasks. In this case, the task duration is almost 1 millisecond. 1 millisecond by the task to process this 1 megabyte of data is at most 1 millisecond. And we already know that the scheduling overhead is also about 1 millisecond. So we can say that the half of the purple part here in Dask is all overhead. Fortunately, this is not the case in large tasks where, as we can see, most of the time is spent on waiting for the data, and the workers are idle for 75% of the time. We notice also that the time spent on sending the data and the metadata is almost the same for small tasks. This can be explained by both the network latency that hides the actual time of sending them, as well as the number of requests that are sent to the scheduler in both cases. So all of that slows down the scheduler. So the metadata transfer, we can see that here, becomes 7 times longer when increasing the number of processes only with a factor of 4. But it's still less than 1 second. And for large tasks, we even don't say it for the first case, and for the other case, it only represent at most 1% of the whole iteration. So for large tasks where the latency and the overhead and all these overheads are hidden, we see that the data transfer here, this part, are more stable while sending 4 times more data. This is explained by the fact that DEISA relies on the network bandwidth to transfer the data that scales with increasing the number of worker nodes, which is not the case, for example, for the disk bandwidth. Yes, so that was all for this slide. I wanted to add one point, is that in another version of DEISA, the actual one, actually, we don't even talk about metadata transfer, so no overheads anymore. And this is better because the scheduler will not be anymore a bottleneck if we go to further experiments. So finally, we arrived to the conclusion. So in this paper, we talked about leveraging task-based programming model for in-situ processing by bringing together the BSP paradigm and the task-based programming model. This shows both an ease of use and a performance gain compared to the post-hoc version with almost the same efforts, which is really interesting from the application people point of view. For the next steps, we're gonna use DEISA for production use cases, namely for Gisela, and we will work on supporting hybrid in-situ in transit workflows, as for the moment we are just doing in transit workflows. Thank you for your attentions, and if you have any questions, please go ahead.